Number 5.
Okay, so I can't make that any bigger, so I'll just rewrite them. Your problems may have had different numbers, but the same structure of the problem. So this first one, I have e to the x to the fourth y equals 7x plus 5y plus 8. Okay, so the idea behind an equation like this is that y cannot be written explicitly as a function of x, meaning we can't really get one expression of x's that would always spit out the corresponding y. Okay? But even though that's true, that it can't be done, we pretend that it can be done. Okay? But still, we pretend that y is a function of x, because when we get to finding the rate of change of y with respect to x, so anytime there's a y, then we pretend that it is some function of x, which necessitates what? A couple people are saying the chain rule, okay? So even though it can't be written this way, it's like they're so intertwined that we can't get the y out and get an expression of x, right? They're locked together by the complexity of the relationship, okay? But we have to kind of pretend that's true because we're going to need the chain rule every time we get to wanting the rate of change of y. Okay, so basically the idea is that we're going to, if those expressions are equal, then their rate of changes are equal, right? So rather than in your mastery test you applied the rules to the x expression. Well, now we don't have a particular x expression, so we say if those expressions are equal, then their rate of change with respect to x's are equal. Okay, and then we apply the rules term by term. Okay, so overall structure of e to the x to the fourth y. So it's e to the something, right? And our rate of change is e to that something, right? That's how it starts. Are we done? Times product rule. Okay, derivative of the first times the second plus the first times the rate of change of y, which would be 1. But then by the chain rule, if y is a function of x, then we'd also need the rate of change of y. So there's our e with chain rule, and that chain rule is product rule, and within the product rule we have the chain rule again. Okay? Right hand side, rate of change of 7x with respect to x. Easy. Rate of change of 5y. 5 by the chain rule now. So I'll be using y prime just for makes the writing a little quicker. Rate of change of 8 with respect to x. 0. So now what we want to do is we got to expand out all our terms, and then every term that has a rate of change or y prime in it, a rate of change of y with respect to x, those terms will go over to the left. Everything else goes over to the right. So we'll expand out. Can I do that all in one step? So can you imagine this multiplied to these two? So what's going to stay over here? This second one will stay. All right. So what will stay? X to the fourth, or e to the x to the fourth y times x to the fourth y. That will stay over here. This will move over. And then what will be left on the right? So I'll have the 7. And then when I multiply this one, right, this will subtract on both sides. So I'll have minus e to the x to the fourth y times. Need some room here. 4 x cubed y. Almost there. So our whole point was to find the rate of change of y with respect to x. Right? So this is the same thing as y prime. So can I do two steps again at once? Is it okay? What I'm going to do, I'm going to factor out y prime, and then what's left is going to be divided. So what will we have had over here? We'll have e to the x to the fourth y x to the fourth minus 5. Anybody have a question on that process? Okay, was there a part 2 to this one? All parts showing. All parts showing. So I'm not going to put this in, and we'll just stop it there, because I think, unless you caught a mistake. Anybody have a question on this? So let's I'll put this original curve in. So E, see what this looks like. E to the x to the fourth y equals 7x 5y. So let's see if there's something cool to look at here. Oh yeah. Okay, and so let's just zoom out a little bit. We'll do that. Just trying to estimate. Okay, so slightly interesting. So let's see here. How about we get -1 here? Okay, that's the closest I can get. So I got the point -1. .627. Okay, and then let's do another point here. How about 1.5? Yes, I'm just making up examples. There we go. 1.5. Nothing. Yeah. .5. 0.606. Okay, so by looking at the graph, I want you to. Can you see that? So just by observation, can you predict what the rate of change of y with respect to x is at each of these points? And then after you make your prediction, we'll plug it in and we'll see how your prediction was. So you can do it by yourself or do it with someone else. But here at -1, 2.627 and 1.5, 0.606, predict the rate of change of y with respect to x. Go. If you don't know what to do, then find someone to work with. So this is a visual exercise, visual conceptual exercise, predicting what you think the rate of change will be. You're not doing any calculations. It's a visual exercise. You guys don't sound like you're doing the task at hand. How's it going? You done?
No, he said it's visual. So you don't want us plugging numbers in?
No, this is a visual, conceptual exercise. By looking at the graph, forget about all this. By looking at the graph, predict, make an estimate of what you think the rate of change of y with respect to x would be.
Less than x equals -1 because it's a vertical line, almost.
Okay, so Daniel and Olivia, you guys talk. Richard and this Daniel, you guys talk. Get a partner. Everyone get a partner and talk about it.
It's going to be almost the same. So it's really only like this much. But it's still pretty close to if we had x equals something not right, because we have the first one, x is -1.
It's small, 0, 0, so y.
You think it's a y, but like 1. But if it's y equals 1, it's this way.
Okay, so this idea we've been talking about all semester long. So we just keep practicing it until we get it. So anyone think they've got a strategy for visually predicting what the rate of change at those 2 points is? Not just one person? Tyler, thank you for saying yes. So, which one do you want to work on?
Take the one on the right, because in this one, I just kind of think of like a tangent line, how that would be set up.
Okay.
Through that one point and only that one point.
Okay.
And since it's coming down on the little slope right there,
Yeah.
it would be a more negative line, but it's not going to have more input, so it's not going to be very negative, like maybe -2, -3 slope.
Okay, so, all right. So why is it that you're thinking about slope? What does that have to do with everything we've talked about?
Because it's the rate of change, it's the relative size of y in relation to x.
Okay, relative size of y. Relative size of what?
Change in
Relative size of change in y to.
changes in x.
So he mentioned that this might be negative for this point. Agree?
Yes.
So why negative? Because, so what do we start with? Do we start with a change in y or do we start with a change in x? Change in x. Okay. A big change in x or a little change in x? Why not a big one?
It's like 0.6, so you know it's not going to be that much.
So in some circumstances, it doesn't matter how big of a change of x you make. Why does it matter here?
Well, you don't know where the next part of the line is going to go. Because, like, if you were to go from -1 to 1.5,
Okay.
I mean, your rate of change is completely different in those two areas.
Right. So what's happening to the rate of change? It's changing, right? If it were constant, then we could pick any delta x we wanted. Right? But the rate of change is always changing because it's a curve. So this using the idea of constant rate of change on a curve only works for small change in x. Okay, so I'll go draw as small as I can so you can still see it. So now we're going to do a change in x. So right around that point, what do you expect the change in y to be relative to that change in x? First of all, is it positive or negative? Negative. Is it a lot smaller? Is it about the same? Or is it a lot bigger?
It's going to be small. About relatively
So Right around there. About the same, a little bit smaller, a little bit bigger. So what would you predict this rate of change, or the relative size of a change in y to the change in x to be? Negative 2/3. Tyler, what were you going to say?
I was going to say like -1. They look about the same.
Okay, so we've got -1 and we've got negative 2/3 because they look about the same. Okay, let's do it. So we want 7 minus e to the x to the 4th. Let's do a to the 4th. So we can just put in different values of a and b. Times b. Times, thank you. 4a to the 3rd. B. Is that our numerator?
Divided by
Oh, 4. No, I forgot an a cubed, right? Is there a cubed in there?
yes.
Now do I have it?
Yes.
Divided by? The same thing again. Should love copy and paste.
But that's e to the 4th.
Yeah, I'm just going to change it.
Minus 5.
Minus 5. Okay, so right now, what's it telling me for, what is this? Yeah, but what's 1.69?
The rate of change. Things A
If a and b is equal to 1.
Yeah, and is 1, 1 a point on this graph? Probably not, right? 1, 1 is probably not a point in this graph. So we have to make a equal to 1.5, and b is equal to, here's the moment of truth. What are we expecting? About -1, I would guess. We got everything right? I don't see any mistakes. 1.5.606. Okay, so we were a little low. It's -1.6, meaning that the change in y is greater. So let's just go ahead and zoom in on that, and we'll see it a little better. So, bigger change in y or smaller change in y than the change in x? Bigger. That's what we're. So that confirms it. So now, for a change in x, change in y is like 1.5 times, or -1.5 times, or -1.6. And that by zooming in on it and getting it small enough to see the linear portion of the curve, that is confirmed. Okay. So the meaning of these rates of change values. And what is delta y over delta x graphically? That's our slope, right? That's our slope. So Tyler, you started with slope, which was correct, but we want to start with looking at changes in x and changes in y, and then talk about slope in the end. Okay? All right. So what if we wanted to graph then the equation of the tangent line at that point? How would we do it? So now I want to graph a new line. That's, if I zoom out, it'll be the tangent line through that point, -1, -2/3. Yeah, use that point slope formula that we developed back in February. Y equals negative. Yep, so 3. -1.63 times x minus 1.5. This is a big advantage to this. The point slope formula is there's no work to do. Once we've done all the hard work to understand it and build it, and so now we've got the point and the slope, we just plug it in. So we should get, notice you can't really see the difference right now. If we zoom out, Oh, bummer. So. So this line then goes through the point in question and has the same rate of change as the curve at the point in question. So this is called the tangent line. It has the same rate of change, but it's a constant rate of change, right? So this is it shows very well why we can't make delta x large. Because if we make delta x a large value, and we take that rate of change, negative 1.6, say I make delta x like this. According to the rate of change at the point, what will delta y be? All the way down here like this, negative 1.6. Does it get us anywhere close to what the curve actually is? No. So that's why when you have a changing rate of change, this reasoning, this constant rate of change reasoning is only good for small changes in x, you see? Because what we have is called local linearity. Local linearity of the curve means if you zoom in far enough, every curve will eventually look straight. And we can apply constant rate of change ideas. Okay, but I lost this point over here, so I think I've got everything. So let's do it for this one. Okay, close enough, 1.001. Let's get local linearity for this one. So I'll let you make your prediction after I zoom in rather than before. So this is our point 1, negative 1, and 2.6. Predict the rate of change. Go. Get your partner. Predict the rate of change. Daniel. It should be. Yes, it is. The scale, the numbers are showing every point 002, both on the x and the y. And that, yeah, that's important for making a prediction, right? If the scales are off, that changes it. Yeah. Okay. How about Andrew, back in the corner? Make a prediction for the rate of change on this one? Or just maybe a general, just a general statement about it?
It's the positive value that's
Rather large positive value, right?
Maybe like 3,000.
3,000? That's a little too big maybe. But for a little change in x here,
Well, I used
what, did you do some numbers?
well, like at the bottom, you see where the line, and then there's like it has the axes. So I just took that distance, like the deviation,
Okay.
at the bottom of it, and then it looks to be about like point 0. What did you say those increments were 0.2 or 0.1?
0.002.
0.002. Oh, okay. Well then yeah, it's probably like 1,500 then or something.
But look at what you're looking at though.
Oh, I was using the bottom one,
But you got to use them both. So can we make a prediction? If you change x a little bit, what's the relative change in y to the change in x? Is it 2?
Oh, that's
Is it 100? What do you think?
I think it's like 10.
Judith says it's about 10. So we could kind of mark them off here. Here's our delta x. It's about this much. That's 8, 9, 10, 11. So my drawing is not perfect.
That's 2.
Maybe between 10 and 20? Or 10 and 15 maybe? 10 to 15? Let's try that. So what's our A and what's our B? So now, this is the great thing about graphing calculator. If you can get in the habit of using this instead of your handheld, this is where it has power to make your life a lot easier. All I have to do now is what? Just change the A and B. -1 and... Oh shoot, I forgot what it was. What was it again?
Where's -1 coming from? 2.6 something.
Arg.
648. Yes. No.
641.
I was in the wrong spot anyway. Wow. Just gonna zoom out once. Shit. Sorry. I can't seem to. There we go. Close enough. 2.6. It's actually 2.66. 2.66. There we go. 17. Okay. So for what does that number mean? Tell the person next to you exactly what that number 17.1. What does that number mean? Tell the person next to you.
That's how he wants to say it.
What?
No, so that's how you want it to say it, right? For changes in y or 17.1 times greater than changes in
Not greater than
time.
times. Right. So, Marcus, say it.
Changes in y are 17.1 times.
Yeah, changes in y are 17 times the changes in x. So as x changes a little bit, how does y change? It shoots up 17 times as much. And that's the rate of change. That's how fast y is changing with respect to x. For a little change in x, y changes 17 times as much. And then so what's the slope then? 17. So the slope is really steep because for a little change in x, y just shoots up 17 times as much. Okay. Anybody have a question? So we don't have time for all these, but let's do some more. So there's number 5. This is e to the 8x equals sine. Number 6, that doesn't look too bad. And there's number 9 and number 10. So 9 and 10 involved. Should we do 10? Let's do 10. Okay? First term. So we're going to go through each term and apply the rate of change with respect to x. Overall structure. It's a product, so we do product rule. So we want to do the derivative of the first times second plus first times rate of change of the second, but we got chain rule. Same thing. So we'll break it up this way. We'll make this the first and this the second. So we start with rate of change of the first, which is 18 divided by 2. 9x to the 1/2. Times the second plus the first. Rate of change of something to the negative 1/2. Negative 1/2. Y to the negative 3/2. Chain rule. Equals 0. Okay, so I went through that fast. This is the last example that we'll do. Unless anybody have a question on that. So what do? We gather which ones are going to stay. This one? Nope, that'll go over. So we're going to keep this one. That will go to the right. Is this one term or two terms? I'm hearing 1 and 2. This times this times this. All one term. It's not added inside the parentheses. It's all one thing. So there's no distributing. So the 2 that I've underlined will stay, and the other 2 will head over, and we can factor out before x. This will be minus 3 x to the 3/2, y to the negative 3/2, y, oh sorry, that's gone. Check my math. So I did 6 times negative 1/2, those are negative 3, and then x to the positive 3/2 and y to the negative 3/2. Factored out the y prime. Right hand side, negative 4y minus 9x half and divide. So these were the ones that lots of you missed, or the majority, or the highest miss rate. Did I lose you? If I lost you, please ask a question.
So when do you know when to not split up an equation like 6x to the 3/2 times all of that? When do you know not to split that up?
It's the difference between A times B times C and A times B plus C. How many terms is that? That's just ABC, right? And what about this? That's 2 terms. It's A times B plus A times C. Does it help? Other questions? So maybe did my parentheses throw you off? Just because you put parentheses doesn't mean you're going to distribute. It just means I'm gathering this stuff together, and this is times, not plus. Okay, does that help? Other questions on this one? So let's first find this. We know that the slope is going to be what? The rate of change of y with respect to x. So let's find it for this one. Let's actually do the numbers first. So negative 4b minus 9a to the 1/2 y to the negative 1/2. Thank you. Thanks. Over 4b. Please come back. Thank you. You only get one undo in graphing calculator. Have you noticed that? You can't do it like a bunch in a row. 3a. I just was typing and not looking. That's what I want. Do I have everything right? What's the point in question? The point in question is 1, 1. So what do I need to do? Set A equal to 1 and B equal to 1. Do I need to do that?
Yes. I think so.
I don't have to do that. Why not? Because if you don't specify it, what are they? They're 1, right? They're asking us about the point 1, 1. Graphing calculator is on by default. If you don't specify, they're 1. So we got it. So at this point 1, 1, I want you to draw that part of the curve. So we're going backwards now. First we get the rate of change. Now you predict what the curve will look like around that point. Okay? So what will it look like? This curve will go through the point 1, 1. So what will the curve look like close to 1, 1? What's that? It's going to go like a downward slope. Kind of like this? What do we think? So someone was saying like this. Is that a rate of change of negative 13? Is it close? It's not even close, right? Well, what should it be? For a little change in x, we're saying, what happened? What's the change in y? Negative. Is it just negative 13? Times that, right? Negative 13 times that. Okay? So, more accurate here would be something heading down very steeply. But as soon as we get away from 1, that can change, right? So that's only really true. The graph will only look like that close to 1. As soon as we get away, it might do this. It might curve back around this way. We don't know.
So it has to be essentially 1 close to 1 in order to say.
Because the point in question is 1, 1. Because the point in question that we found the rate of change at is 1, 1. It's only close to x equals 1 that we can say the graph is going to go down steeply like that. Negative 13 times as fast as a change in x. Okay, last chance for questions on these problems. From yeah, ask.
So on this problem,
Uh-huh.
when I was doing the homework, I got it incorrect, and it said that it was, on top it said it was 8y, and on the bottom it said it was minus 8. Like, it said it was an 8x, and I don't know why it, like, doubled it.
You made some algebra error.
Yeah.
So we just had to sit down and work through it. And I'm happy to do that with you. So you just made some kind of math or algebra error, and you ended up with the wrong number.
Okay.
Okay.
So then the process is finding that negative 4y minus 9x still have 1/2, finding all of that, and then plugging the point in to find the slope of the line at that point.
Well, what is the slope of the curve? That's the rate of change. How do you find the rate of change? So it's all about it's that you don't have to memorize kind of steps.
That's the process that we just went through.
Right, we found the rate of change by using implicit differentiation. So we got an equation for y prime equals.
And then plugged in x and y.
So that was some function that had x's and y's in it. Okay? And now, if you've got a point on your curve, say 5, negative 6, how do you get the rate of change at 5, negative 6? Boom, plug it in. That's what that equation does. It gives you the rate of change at any point on the curve. Yeah. And then that rate of change graphically then is the slope. Because it's the change in y over the change in x. Okay. What do we got here? So I want to do, now I want to look at, let's look at an application here. Okay, so there's a ladder. It's red. It's up against the wall, and then there's this real tricky monkey He likes to kick that ladder out. And every time you put it up, he kicks it out. All right. So we want to, if this is still the x-axis, and this is the y-axis, we want our x to be, what does the x-coordinate of this point represent in the context? So this point right here is the x-coordinate. So what?
Feet from the wall, or distance from the wall.
Yeah, distance of what? Bottom of the ladder from the wall. Is that a changing quantity or a constant quantity? Changing, right? So it's moving out to the right here. What happens to x? What does that quantity do? Just in general. Increases from 0 to 10, okay? Increases from 0 to 10 in this context. All right, what is y? Distance from, yeah, so distance from the ground to, I should actually switch these, but it's the same. So distance from the ground to top of the ladder. And in this context, what does the quantity y do? Goes from 10 to 0. So if we wanted to talk about the rate of change of y, it's supposed to be a y, with respect to x, what would we need to come up with? So these are two quantities changing together, right? X is going from 0 to 10 as y goes from 10 to 0. So we could talk about the rate of change of y with respect to x. What would we need to formalize that, or get an equation for the rate of change of y with respect to x? What would we need to start to do that? Can we just write it down? Can we just say, oh, well, it's y prime is, it's one of these, like, e to the x cubed minus 8y plus 2. Can we just write it down? How can we get that? How can we get something like this that will give us the rate of change of y with respect to x? What's that?
You're going to need points.
Need points.
Like on the, as you're going down, you're going to need to.
Freezing. Well, we know the first one that.
Okay, so you kind of want to build it point by point, but I'm asking for an equation. Then all we have to do is plug in a point and it'll spit it out. Autumn.
We're not gonna get just like the equation right off the bat, but I think you can use like, since it's like a triangle, you can use like some kind of standard equation. Like
Equation involving what?
well, it's a right triangle, so you could use like the Pythagorean theorem maybe.
But what quantities do we want to involve in that equation so that we can get this?
X and Y.
Yeah, so in order to get a rate of change equation, where do they come from? They come from a, what's that? Yeah, we have to start with another equation that brings x and y together, and then we can do our implicit differentiation, right? So how do we get that? So let's just pause it here. So this type of thing is going to come from just like all your homework problems, right? How did you get these rate of change equations? You had to start with an equation that showed the relationship of x and y in the first place, right? So it comes from an equation of x and y. So in this context, I've got it paused right here. What is our x value?
Right now it's
9.5 or something like that. It's from here to here, right? It's this distance right here. And what's our y?
At the moment, maybe it's
3.2.
Yeah, maybe it's around 3 or 2.5 or something like that. 2.8. Okay. So can we get an equation that brings together x and y? Yeah, what is it?
Equals whatever. This is
And what we know what that is. What is that? No, remember what does x do and what does y do?
X increases and Y decreases.
Right, but we're asking how long this is right here, right?
10 feet.
It's got to be 10, right? So x squared plus y squared equals 10.
Squared.
Not 10 squared, but it's just
Pythagorean theorem, 10 squared. Is that true no matter what x and y are?
Yes.
What about now? Does x squared plus y squared equals 10 squared? Yeah, just a different triangle, but the relationship holds. So we got this relationship that holds, and from it we can get the rate of change of y with respect to x. This is a really easy, fast one. Do it. Get the rate of change of y with respect to x. You can do it. Good. So get your rate of change of y with respect to x.
okay. Got it.
Judith, did you get it?
But I don't want to explain this to class.
I'm sorry, you don't have a choice. What'd you do?
Okay. Well, the rate of change with respect to x is 2x.
2x?
And then it's plus 2y.
2y.
You have to do chain rule, so it's dy dx or y prime.
Okay.
And then the derivative of that is 0.
Okay.
So then you get y prime by itself, so you subtract the 2x.
Okay.
Divide by 2y. And it's negative 2x over 2y or negative x over y.
Did you get that?
Yeah.
Cool. All right. See, that wasn't so painful. You did great. Very good. So now I'm going to come over here. I'm going to try to make x about 9. No, I want 8. Sorry. Y, yeah, y 8. Okay? So I got y equals 8. What's the rate of change right now? Y equals 8. What's the rate of change of y with respect to x right now? 8, negative 8, negative 1/8, negative x over 8. What's that? Negative 5 over 8. How'd you get that?
It's a little bit bigger.
Okay, so she's looking at x and saying, oh, well, when y is 8, x is 5. Is it 5? Can you get exactly what it is? Can't? Can't get exactly what it is?
Now, if you're getting the value for x, but you're not.
Yeah, Daniel.
You can go back, use the original equation.
Yeah, this is always true, right?
Yeah, put 8 in for y.
Put 8 in for y,
And then solve for x.
solve for x. Yeah, this is governing how x and y change together. So if we know what y is, we're saying y is 8. What is it? Is it 6? So it's the reason it doesn't look like 6 here is because I don't have it at 8 here, okay? So now, what is the rate of change of y with respect to x? Negative 3/4. Okay. One more. All right. Y equals 3. Find the rate of change of y with respect to x. Go. What's the rate of change of y with respect to x?
If y equals 3.
If y equals 3. Someone got square root of 91. Okay. Negative. Let's get a decimal approximation so we have something to talk about. Decimal approximation.
9.54.
Okay, and then divide by 3. Point what? 18? About negative 3.18. Okay, so what story? So we got negative 0.75 and negative 3.18. So these rate of change, what story is it telling as the ladder falls? So what do these numbers tell us about the ladder falling? What's that? How do you know it's speeding up? It's a smaller negative, right? Yeah, so it's speeding up. Okay, that rate of change is it increasing or decreasing? The rate of change?
It's decreasing, but it's increasing in magnitude.
It's decreasing. It's getting more negative, so the rate of change is decreasing. The speed is increasing, but the rate of change is decreasing. Okay, so that means for the same change, for a change in x around when y equals 8, how does y change for a change in x around y equals 8? Does it change more or less than x?
Less.
Yeah, so when the ladder's up here at 8, x changes a little bit, it's going to fall a little bit more or a little bit less? It's going to fall a little bit less than whatever your change in x was, right? Here, when y is around 3, if x changes a little bit, how much will the ladder fall? How much more? About 3 times as much. As x went out to the right, the ladder's going to fall about 3 times as much. So then the conclusion is, Beth said, it's speeding up as it goes down because the changes in y are getting more negative. Okay? So, but we note that the rate of change is not increasing, but decreasing because it's becoming more negative. The speed is increasing. But when we talk about rate of change, we bring the negative or positive into it. So this rate of change is decreasing, although the speed is increasing. Okay.